Lesson 4 looks at real-life applications. In the last few tutorials, we looked at the vertex form of a quadratic function, standard form of a quadratic function, and from standard form to intercept form, factored form of the quadratic function. And what we're going to do today is we're going to get away from just the pure mathy thing, and we're going to interpret stories. So here's example number 1 of a parabolic mirror. And normally what would happen is, and the first thing you'd want to do is you want to impose a grid onto the story, because that's what we've been doing. We've been using XY axis and making the equation of a parabola. And that's what we want to do in these ones as well. We want to impose a grid onto the story. So right here, you're given a certain piece of information that makes this one really helpful. If the vertex of the mirror is at the origin, so what we could simply do is we could sketch, and I'm just going to sketch our XY grid onto our question. And here's our vertex right here, and given the story, here's our 3, 1, and here's our -3, 1. And those become important. So here, we would simply now want to write the equation, and we can write the equation in any way we want, but given we have a vertex, I think vertex form is the way to go here. So I highly recommend when you start these kind of questions, you write down your form of the equation. Makes everything a lot easier. We know that the origin is at 0, 0, so P and Q are 0 and 0. And what we then have is this simplified version. And again, remember, X and Y represent any coordinate in our story. So it doesn't matter which one you pick other than the vertex. Everything turns to 0. We just want to enter our coordinates and solve for A. And when we go ahead and enter a 1, and I'm going to use the positive 1, we end up with A is equal to 1/9, which makes sense because it's positive. It's open. This mirror is opening up. It looks kind of squashed, so therefore it's a fraction, and our equation is equal to 1/9 x squared. So again, key ideas: superimpose a grid onto the story, choose the form that you think is going to be easiest to solve, and then go ahead and practice the techniques we've been learning. Okay, landscape bridge example. Again, in this picture right here, given the information in the question, standard form and factored form might not be the way to go, because we're told something, two things relative to the water surface and again above the water surface. So we're given information about the water, and then we're given information about the bridge. So based on this story, it probably makes sense to make the water the x-axis. And now if you look at this, if you look at the bridge, there are no x-intercepts, therefore factored form is not the way to go, and that only leaves vertex form and standard form. Now the other thing we have to decide is where to put our y-axis. So we could put the y-axis in the vertex, because there is enough information if the vertex is in the middle, so we have enough information. But I'm going to choose this pylon right here to be my y-axis. Again, you might choose the middle, the vertex, but I'm going to choose that. So here's what I know then. Based on the story, I know my x-coordinate for this point is 0, and I know the towers are 111 meters tall relative to the water, so I know that one 0, 111. I know that my towers are 472 meters apart, so this one would be 472, 11. I know the vertex is in the middle, so it's 236 meters, and the story tells me that it is 67 meters above the water. So again, in this question right here, if I'm given the vertex, or if I understand that I'm given the vertex, then vertex form is really probably the way to go. So what we can then do is, I'm going to go ahead and I'm going to use vertex form. And again, I'm going to substitute my values of my vertex, 236 squared plus 67. And then I'm going to choose one of the values. And again, it doesn't matter which one you choose other than not the vertex. So the one I'm going to choose in my calculation is this one, but you could have chose the y-intercept as well. But again, it really doesn't matter. You're probably going to need a calculator to do this. So when we plug in 111 is equal to A, 472 minus 236 squared plus 67, we get 111 is equal to 55,696 A plus 67. We subtract 67 from both sides, and we divide both sides by that 55,696. So this is a ridiculous number, but honestly, in the real world, numbers don't always work out super nice. 696, and whatever that equals, and I don't care, because I have figured out all of the pieces of information, A, P, and Q, just like you did a few days ago. And there is the equation for the cable that runs down from the two towers. Okay, let's look at another example, a fencing example, a box example. They're classic. And one of the reasons I chose this example is it's always a good idea to draw a picture that really helps your brain. So she wants to build a rectangular enclosure. So here's my rectangular enclosure. I draw all my rectangles look like that. The perimeter is 24 meters of fencing, and I'm going to label my L and W. And again, we want to write a function that represents the area, and she wants the biggest possible area. There's a whole bunch of different dimensions that we could have, but we want to have the biggest rectangle. So our formula for the area is really simple: L times W. But there's a problem here. There are two letters, and we only want one letter. So what we're going to have to do is we're going to have to get rid of one of those letters, and it doesn't matter what it was, what one it is. So what we can go back to is we can go back to this perimeter information, because from grade 4, grade 5, whenever you learn that, you have this little formula for the perimeter of a rectangle. And we know certain things. We know that the perimeter of this particular rectangle is equal to 24. So again, given we know that, what we can then go ahead and do is choose a letter to isolate and then substitute it into our area formula, and then we'll only have one letter. So I'm going to choose to get rid of L. So in choosing to get rid of L, I'm going to subtract 2W from both sides, and I'm going to divide everything by 2. And when I do that, I get L is equal to 12 minus W. And what I can then do is substitute that into my area formula, and that would be a function that would figure out the area of any rectangle given this story. So for example, if we made a quick little table, if the width were 1, then the area would be 12 minus 1, which is 11, times 1, which is 11. If the width were 2, then 12 minus 2 is 10, and 10 times 2 is 20. If the width were 3, then 12 minus 3 is 9, and 9 times 3 is 27, and et cetera, et cetera, et cetera, et cetera. And one of those numbers would be the best. The area would be the biggest. Well, if we wanted to understand this pictorially, well, instead of having A's and W's, we could simply have Y's and X's. So we could write something like this. And if we expanded that, that would be 12x minus x squared, or negative x squared plus 12x in standard form. And what we could then go ahead and do is we could draw a picture and understand what the value of say a picture is, what the value of the vertex is. So in this example right here, if we went ahead and drew this picture, well, here's what we'd have: our y and we'd have our x. And again, from this right here, factored form, we'd find our two x-intercepts. And our x-intercepts would simply be 0 and 12. So in the example above, I actually haven't gone out ahead and figured out the answer yet. You know, what would be the dimensions that would give us the biggest area. But given I have my x-intercepts at 12, what I know is the axis of symmetry is exactly in the middle of those. And based on this leading thing being negative, I know my parabola opens down. I know I'm going to have a top. And a top is the most. The top is the maximum. And all I have to do is figure out what is the y-coordinate when x is 6, and I get 36. So the vertex, the coordinates of the vertex are going to be 6, 36. And again, in this question, the vertex gives us the answer, because we want to know the maximum. She wants to build a rectangle with the maximum possible area, and the very top is the maximum value of this story, this equation. So what does the coordinates of the vertex represent? Well, again, remember what x represents. X represents the width, and y represents the area. And what the vertex represents is the dimensions that will give the maximum area. Squin, it's this idea of making a word story into a mathematical story and using the ideas we've been learning as we've been going through. So one last one, a revenue question. So again, this kind of question just depends on you understanding a basic idea. The more you sell something for, the less people buy it. The less you sell them for, the more people can buy it. But there's going to be a point where you can sell some product for the best possible price that will generate the most revenue. So that's the general idea. You're going to sell something for a particular price. A number of people are going to buy it. If you sold it cheaper, you'd sell more. If you sold it for more, you'd sell less. And we just want to figure out the just right price. So here's a story where here's the information that's known. A survey indicates that 50 fewer students will buy a membership for every $1 increase. And here's our base information right here. So basically, what this is saying is, for every dollar above $6 you sold a membership for, you're going to get less students buying it. And based on this story, we might want to determine, well, at what price should we sell our memberships so we generate the most revenue? So our first question would simply be to write the revenue function as a function of x. So again, x are the number of increases, and the price is the initial value plus $1 increases. So x is the number of price increases. And what that would give us is our initial 700 people would be reduced by 50 people for every price increase. So that's what the yellow highlights. Every time we do an increase of $1, we lose 50 people. And you might think right now, maybe we should sell it for less, and then we'd increase the number of people, and that's what we want to see. So in this story right here, what we can do is we can FOIL this out. And when we do that, we get a quadratic, and I'm going to put it in descending powers. And this is another way of writing our revenue function. So what this says is, remember we had $6 a year and 700 people, that's 4,200. So that's what this says. If we had no price increases, if we left things the way they were, then we'd have that amount of revenue. But if we increase the money by $1, we would actually generate more revenue. And you could plug that into your graphing calculator if you want right now. But here's what I want you to see. You have a parabola that opens down and has a y-intercept of 4,200. So if we were going to do a quick little sketch, this thing would have a y-intercept and of 4,200, and the picture would kind of look like that. So if you enter that into your calculator, that's what you're going to see. But we don't even have to do that, because as we've just recognized, the vertex is going to indicate the best possible solution to this question. And we have a nice little formula to figure out the vertex. And the vertex, the x-coordinate, the axis symmetry, is equal to negative b over 2a, which is equal to negative 400 over 2 times negative 50, which is 4. And when we figure out the y-coordinate, when x is equal to 4, well, the y-coordinate, when you plug that into our equation, you could plug it into this one right here, or you could plug it into this one right here. What you get coming out is 5,000. And what that means is the vertex is 4, 5,000. Now remember what this represents. X coordinate represents the number of $1 increases. So basically, what this vertex tells us is when price increases by $4, we get a maximum revenue of 5,000. So that's what that means. Now remember, when we had no price increases, we had a revenue of 4,200. So what this one says right here, when we have 4 increases of $1, so when we bump the ticket price up from 6 to 10, we lose 200 people, but that's okay. We're making more money. Now, everything after that, when you bump it up by $5, $6, then your revenue starts to decrease.